Hello, good afternoon. Last time we have seen some properties of asymptotic notations, and we had also seen the growth of the functions. Just take a quick review of this. What is big O notations, what is big omega notations, and what is theta notations. So this is the first notation, that is order of notation. F of n is order of g of n. Here we can see that c times g of n is always greater than as compared to f of n. So basically it is used for providing the upper bound. Then this second is f of n is omega of g of n. Here we can notice that c times g of n is smaller as compared to f of n after some predefined value of n0. And this omega notation is used for providing the lower bound, and this is the theta notations. Here basically f of n is in between of c1 times g of n and c2 times g of n, basically used for providing the exact bound. The growth of this f of n is lies in between of these two functions. Then we had seen the growth of the function where n was this, and these are the functions in terms of n, like log n square, n cube, and 2 raised to power n. This is the growth of the functions. First constant is there, then this order of 1 is less than order of log n, then order of n, it is less than or equal to order of n log n, is less than order of n square, is less than order of n cube, is less than order of 2 raised to power n, is less than order of 3 to the power n, is less than order of n to the power n. Okay, these n square, n cube are the polynomial functions. These 2 raised to power n, 3 to the power n, these are the exponential functions. So the growth of exponential functions is larger as compared to the polynomial functions. Then we had seen the asymptotic notations, small o and small omega. The bound provided by asymptotic notations, small o and small omega, will not be asymptotically tight, means the growth of these two functions will be different. Then we had seen some examples. Then today we will see the various properties of asymptotic notations. See the first property, if f of n is order of g of n, if this is given, then a times f of n is also order of g of n, where a is some positive constant. We can see one example of this. Suppose f of n is 2n square plus 5u. Okay, then it is order of n square because the dominating term is n square. If we multiply this with the help of some positive constant a, so 7 times f of n is nothing but 7 times this 2n square plus 5. Okay, so this will become 14n square plus 35. This is also order of n square because this growth is larger term here is n square. Similarly, this property is also satisfied for omega notations as well as for theta notations. Like if f of n is theta of g of n, then a times f of n is also theta of g of n, and if f of n is omega of g of n, then a times f of n is also omega times g of n. Okay. This is the first property. Then second property is known as reflexive property. What is reflexive property? If f of n is given, then f of n is order of itself. That is nothing but the reflection of the same functions. Okay. So this reflection is true for order of notation, omega notation as well as theta notations. If f of n is given, then f of n is theta of f of n as well as f of n is omega of f of n. Then third property is important, that is known as a transitive property. Transitivity means suppose A is related to B and B is related to C, then how A is related to C, that is known as transitivity property. So what is transitivity? If f of n is order of g of n and in turn g of n is order of h of n, okay, then so f is related to g is related to h with the help of this order of. So with the help of transitivity, we can say that f of n is order of h of n. See one example. Suppose f of n is n, g of n is n square. So f of n is order of n square, that is correct. And h of n is n cube. So g of n is also order of h of n. So in that case, we can also say that f of n is order of h of n. Okay, n is order of n square is order of n cube. Then we can also say n is order of n raised to power 3. So this is n and this is n to the power 3, as this order of is providing the upper bound. So we can say that this is also correct. But the asymptotically it is not tied. What do you mean by this? The growth of this n will be smaller as compared to n cube. Similarly, this property is satisfied by both omega notations also and theta notations also. So in terms of theta notation, is if f of n is theta times g of n and g of n is theta times h of n, then we can say f of n is theta times h of n, as well as if f of n is omega of g of n as well as g of n is omega of h of n, then we can say f of n is omega of h of n. Okay, so this is the third property, that is known as transitivity property. Then we will see the fourth property, that is the symmetric property. What is symmetric property? If f of n is theta of g of n, then g of n is also theta of f of n. Okay, so this property will be applicable only in case of theta notations. Okay, because theta notation is used for providing the exact bound. So f of n is theta of g of n, then g of n is theta of f of n. See the example, both are n square. So we can say f of n is theta of g of n, theta of g of n is also theta of f of n. Okay, but this is not true in case of order of notation or in case of omega notations, because if we take one example of order of notation, then we can say that n is order of n square, but vice versa is not correct. We cannot say n square is order of n. Okay, then the next property is transpose symmetric property. What is transpose symmetric? If f of n is order of g of n, then g of n is omega of f of n. Okay, that is correct. Smaller function is always order of larger function, then we can say larger function is omega of smaller function. That's what we are saying here. So this property is satisfied both for order of as well as for omega notations. Okay. See the example, f of n is n and g of n is n square. So here we are saying that n is order of n square. That is correct. If n is order of n square, then n square is omega of n. That is also correct. So it is known as transpose symmetric property. Some more properties are there, like see, if f of n is order of g of n and f of n is omega of g of n. Okay, so we can say that f of n is theta of g of n. We had already seen this, because if we are providing upper bound as well as lower bound with the help of that particular bound, then it is nothing but exact bound. So theta is applicable only when this order of and omega is both of them are
तो
true.
वो भी है, वो चलेगा क्या इसे?
If f of n is order of g of n and d of n is order of e of n. Okay, so these two separate functions are there in terms of n. So what is the order of provided for f is g. So f of n is order of g of n and d of n is order of e of n. Okay, so if we sum these two functions, like f of n plus d of n is nothing but order of max of these two. So max of g of n and E of n. So we will take maximum of this and see the example of this. Suppose f of n is n, so it is order of n, and E of n is n square, so it is order of n square. So if we take the addition of these two, okay, then n plus n square. What is the larger term here? The larger term is n square, so it is nothing but order of n square. That's why we are taking here max. Now see the next one. If f of n is order of g of n and d of n is order of e of n, and if you perform the multiplication of these two, like in case of here, if you perform multiplication between n and n square, so that will become n cube. Okay. So f of n multiplied by d of n is nothing but order of g of n multiplied by e of n. See, same example that we are taking. This is n, this is n square. Okay. So if we multiply these two, f of n is multiplied to d of n, then it become n multiplied by n square, so that is n cube, so it is nothing but order of n cube. So these are the properties of asymptotic notations. Then just have a look on the basic searching and sorting algorithms. First, two searching are there, so I have not covered the algorithm for searching. Linear search is very simple. In linear search, we start searching from the first position and we search till the last for any particular element that is provided by the user. So if n elements are there in that particular array, then the best case time complexity is that when you get the element at the first position itself, then it is known as order of one time complexity. And when the element is present at last position or element is not at all present in that entire array, then that is nothing but the worst case, in which how many comparisons are required? Order of n comparisons are required. What is the fundamental operation in linear search? The fundamental operation in linear search is comparison. So basically, for providing the asymptotic notation, we need to count the number of fundamental operations, like how many fundamental operations are there in best case, how many fundamental operations are there in worst case, and how many fundamental operations are there in average case. Average case lies when the element is present somewhere in the middle of the list. Okay, so suppose n elements are present in the list, then approximately n by 2 comparisons are required in linear search. The second variant is this binary search. For binary search, the input should be in the sorted sequence. Okay, so first of all, we will find the mid element and we will compare the element smaller. Then we are interested in the first half of the linked list, or otherwise we are interested in the second half of the linked list. Okay, so every time the list is divided by 2. Suppose initially if consider that 100 elements are there in the list, then after first iteration 50 elements will be considered. After that 25 iterations will be considered, then 12 iteration will be considered, and so on. Okay, so the time complexity of this will be log n, and the list, as the list is divided into two equal parts, so the base of this log will be 2. Another variant in the binary search is the ternary search, in which the sorted list is get divided into 3 equal parts. In that case, the time complexity will be log n, but base of that log will be 3. That is nothing but the ternary search. Now just see this 3 basic sorting algorithm: selection sort, bubble sort, and insertion sort. First, we will see the selection sort algorithm. Selection sort is basically based on finding the smallest element and placing it at the first position. Okay, this is the step 1. Then find the second smallest, place it at the second position. This is step 2. Find the third smallest, place it at the third position. This is step 3. Find the fourth smallest, place it at the fourth position. This is step 4. Last element will find its position automatically. Suppose in this example we are considering 5 elements, then how many steps or how many passes will be required? 4 passes will be required. This is first pass, second pass, third pass, and fourth pass. So in general, if n elements are there in the array, then how many passes will be required? N minus 1 passes will be required. Now see, number of comparison. What is the fundamental operation in sorting? The fundamental operation in sorting is also comparison. Then we need to compare these two elements, like how many comparisons are required in the first step, how many comparisons are required in the second step, in third step, and so on. So see here, first we will take this 20. we will compare this 20 and 12. Okay, which one is smaller? So 12 is smaller. So we will store the index of this 12. Suppose here the indices are starting from 1 onwards. So we will store the index of this 12. Okay. After that, this 12 is compared with this 10. Then finally, you will get the smaller element is 10. Then this 10 is compared with 15. So 10 is smaller. So it will remain as it is. Then 10 is compared with 2. Then 2 is smaller. So 2 comes here. Okay. So you can notice here how many comparisons are required. In first pass, 4 comparisons are required because n elements are present, then n minus 1 comparisons are required in the first pass. This is first comparison, then second comparison, then third comparison, and it is a fourth comparison. Okay, this is the completion of step 1. What we have achieved after the completion of step 1, the smallest element. What is the smallest element here? In this example, the smallest element 2 got its correct position. Okay, once again, the same process will start from the second index. Now we will find the second smallest. What is the second smallest here? How many elements are remaining now? This is the remaining 4 elements. And for these 4 elements, how many comparisons are required? 3 comparisons are required. This is first comparison, this is second comparison, and this is the third comparison. So based on these 3 comparison, we will find the smallest among these 4 elements. What is the smallest here? 12, 20, 12, 15, and 10. So 10 is the smallest. So after the completion of step 2, 10 got the correct position. This is step 2. After that, the same step is repeated for the last 3 elements. So 20 and 15 is compared, and then this is compared. So 3 elements are remaining. For 3 elements, 2 comparisons are required. And lastly, this is the last step in which single comparisons are required. Okay. So in general, if n elements are present in the list, then n minus 1 comparisons are required in first step. In second, n minus 2 comparisons are required. In third pass, n minus 3 comparisons are required. In fourth pass, n minus 4 comparisons are required, and so on. Okay. See the analysis of this. Total number of comparison: n minus 1 plus n minus 2 plus n minus 3 plus n minus 4 plus n minus 5 up to plus 1. Okay. So this is nothing but the arithmetic series from 1 to n minus 1. Okay, and if you get the result of this, then it will become n into n minus 1 by 2. N into n minus 1 by 2 is nothing but order of n square. N into n minus 1 by 2 is nothing but order of n square. So the time complexity for this algorithm is order of n square. Okay, see the worst case time complexity, best case time complexity, and average case time complexity, all are n square. Why all are n square? Suppose see the input is already sorted sequence, then also we will perform these steps. Okay, or first see the algorithm, then the things will get clear. See this outer for loop. N is nothing but the number of element in that list. I is ranging from 1 to n minus 1. 1 to n minus 1 means how many times? N minus 1 times. Okay, so this outer for loop indicates the number of passes or number of steps. So here n is 5. This is running from 1 to 4 means 4 times. When the value of I is equal to 1, we are talking about this step. When the value of I is equal to 2, we are talking about this step. When the value of I is equal to 3, we are talking about this step. And the value of I is equal to 4, we are talking about the last step. Okay, we are considering the index. So minimum is considered as minimum index is stored in mean variable, and initially it is I, and from where we are starting from I plus 1 till n. Okay, if list of j means if element at this particular position is found to be smaller than the list of mean, then mean is updated. Mean is equal to j. Okay, so this is loop is continued, and when the loop is get completed, then we are having a mean which contain the index at which smallest element is present. Okay, then we directly come out of this loop, and if we check that index mean is not equal to I, means this is I, it is stored in mean. Okay, and this index mean is not equal to I, then we will just swap these two. Okay, now two things are there in this particular algorithm. One aspect is the number of comparison, another aspect is number of swapping. Here you can notice that this is outer for loop, this is inner for loop. Okay, So number of comparison, this is the number of comparison here. Less than is nothing but the number of comparison. We are comparing this. So for one value of I, this is running n minus 1 times. For the second value of I, it is running n minus 2 times. Similarly, the total number of comparison will be n into n minus 1 by 2. So the final comparison will be order of n square. But see here, the swapping statement. Swapping statement is outside of this for loop. Okay. And how many times this statement is getting executed? This statement is executed as many times this outer loop is running. And how many times this outer loop is running? This is running n minus 1 times. So the time complexity of this statement will be order of n. Okay. So number of comparison will be order of n square plus the number of swapping will be order of n only. This is the difference between the number of swapping and number of comparison. This is the selection sort. Selection sort is basically based on finding the smallest element and placing it at the first position. Then we will see the second algorithm. Second algorithm is known as bubble sort. Bubble sort is basically based on comparing the consecutive elements every time. So suppose 5 elements are given, then we will first compare first and second. And if it is an inversion, means if it is not in correct order, then we will swap these two. Then second and third is compared. Then third and fourth is compared. Fourth and fifth is compared, and so on. Okay. See first example. Just see this example. How many elements are there here? 4 elements are there. Okay. So first and second is compared. So 4 and 7 is compared here. So these are not in the correct order. So this is swapped. 4 comes here, 7 comes here. Okay. After that, 7 and 5 is getting compared. 7 and 5 is getting compared. It is not in correct order, so it becomes 5 and 7. After that, 7 and 2 is compared. While comparing 7 and 2, this is not in the correct order, so 7 comes here and 2 comes here. Okay. This is nothing but the completion of step 1. Completion of step 1. Here you can notice there is a difference between the number of swapping in selection sort and the number of swapping in the bubble sort. Here we are comparing and we are swapping, but in selection sort we are comparing. Okay, and after doing all this comparison we are swapping only once. This is not the case with bubble sort. We are comparing as well as we are swapping. This is the code for swapping of a of I and a of I plus 1. So this is the completion of pass 1. What we have achieved after the completion of pass 1, the largest element. What is the largest element? Largest element is 7. So largest element got the correct position. Okay. What we had achieved after the completion of selection sort, in selection sort after the completion of pass 1, smallest element got the correct position, but here in bubble sort largest element got the correct position. Then once again we start with the same first and second element. So initially you will get this 4, 5, 2 and 7. After that this 4 and 5 is getting compared, so it is in correct order. Then 5 and 2 is compared, it become 2 and 5. We will stop here because the largest element is already got its correct position. Okay, so after the completion of this second step, what is the second largest element? Second largest element is 5. Second largest element got the correct position. Okay, after that in step 3 only one comparison is required. So 2 and 4 is compared, 4 and 2 is compared. Now it become 2 and 4. So finally you will get one sorted sequence 2, 4, 5, 7. Here 4 elements are there. Then how many comparisons are required in first pass or in first step? 3 comparisons, means n minus 1 comparisons, and as well as n minus 1 swapping. Okay, it depends on the inversion. Whether if it is an inversion, then we will perform swapping, otherwise we will not. Okay, so based on that we will define the best case, average case and worst case of this. This is step 2. Step 2. So first 3 elements are considered in step 2. If first three elements are considered, then 2 comparisons are required. In step 3, first 2 elements are considered. If first 2 elements are considered, then single comparison is sufficient. So n minus 1 plus n minus 2 plus n minus 3 plus n minus 4 up to plus 1. So the time complexity will remain same, n into n minus 1 by 2. And number of swapping, that will also be n into n minus 1 by 2. When you will get this n into n minus 1 by 2, when every time you are having an inversion, means it is not in correct order each and every time. When you will get this sequence, or when you will get this scenario, when you want to sort an input in the ascending order and the input is given in descending order, or vice versa, when the input is given in the descending order here and you want to sort the element in ascending order, then each and every time you will get an inversion and you will just replace these two. Okay, means the number of comparison and number of swapping will be same. Suppose if you want to sort the element in descending order, then what changes will you require in this algorithm? This a of I is greater than a of I plus 1. Only this condition will get changed. If you want to sort it in the descending order, then this a of I is less than a of I plus 1. Then we will perform this change. Okay, so only one sign needs to be changed for arranging the elements in the descending order. Now see one more thing. Suppose you want to sort the element in ascending order and the input is already ascending sequence. Then what you can do? The input that you want to sort it in the ascending order and the input is already given in the ascending order. Then what you can do? You will compare first and second. Will it cause any inversion? No. Then you will compare second and third. Will it cause any inversion? No. Then you will compare third and fourth element. Will it cause any inversion? No. Like this, you will reach to an end, and it will not cause any of the inversion. Okay. On that basis, you can conclude that there is no inversion in any of the comparison. Then there is no necessity of the subsequent steps. So you can define modified bubble sort. And what is modified bubble sort? Once again, it is starting from this. For I is equal to, it is running, this is the Python syntax. It is running from once again 1 to n minus 1, where we are changing this variable swapped. It is a flagged variable. Initially it is true. Okay. Then you will once again comparing this. Array of j is greater than array of j plus 1. If it is true, then you will go here and you will perform this swap. But if you will not get a condition true any of the time, then you will not go inside this if statement. And what will be the final value of swapped variable? The final value of swapped variable will be true only. In that case, no subsequent passes will be required. Okay. So you will come here, then you will once again compare. If swapped is equal to true, then you perform break, means no subsequent passes required after this particular pass. That is nothing but the modified bubble sort. Now see the best case, worst case and average case analysis of this. What is the worst case here? Worst case is same. You want to sort the element in ascending order, data given in the descending order, or vice versa. When the data is given in the descending order and you want to sort the element in ascending order. That is the worst case, in which the number of comparison, number of swapping will be n square, order of n square. Second thing, best case, when the number of you want to sort an element in the ascending order, data given already in ascending order, or when you want to sort the element in descending order and data given also in the descending order, then that is nothing but the best case. How many comparisons are required? Only first pass is required. And in first pass, how many comparisons are required? N minus 1 comparisons are required in the first pass. And how many swappings are required? Number of swapping in best case will be 0. Okay. So n minus 1 comparisons are required. So number of comparison will be order of n, and number of swapping will be 0. This is nothing but the best case. And average case lies somewhere in the middle of this. That is nothing but the bubble sort. So see the analysis of modified bubble sort. Worst case time complexity is order of n square. Best case complexity is order of n. and average case is also order of n square. Okay. Average case occur when the elements of the array are in the jumbled order, neither descending nor ascending. That is nothing but the average case. Next, we will see the insertion sort. See, in insertion sort, each and every time one element is selected, that element is inserted into the already sorted list. Okay. Now, what you will do if you are having a sequence of n elements, then you start from the second element onwards. You find the position of the second element, and if it is not in the correct order, then you will insert it in the correct order. So basically, what you can see first example. This is the example of insertion sort. Okay, so these elements are given. Total 8 elements are there. So first element is considered as a sorted element. Okay, you start from the second element onwards. Now you will compare this 3. This 3 is compared with the 4. Now you will check whether this is in correct order or not. So what should be the correct position of this 3? This 3 should come before this 4. Okay, so what you will do, this 3 should come here. So for this you will right shift this 4. So 4 comes here, then this location is get freed. Okay, then 3 is inserted here. So finally you will get 3 and 4. Okay, so you will get this 3 and 4. After that, this 2 is considered. Okay, now see, this 2 is inserted into the already sorted list. What is the already sorted list? This 3 and 4 is nothing but the already sorted list. First of all, this 2 is compared with 4. Okay, so what should be the correct position of this 4? 4 should comes after 2. So this 4 is right shifted. So 4 comes here. Okay, after that, once again, this 2 is compared this 3. So 2 comes before 3. So once again, 3 is shifted one position right. Okay, then no element is there, then 2 comes here. So what is the sequence become? The sequence is nothing but 2, 3, 4. Once again, you will take this element 10. Okay, so 10 is compared with 4. So 10 should come after 4 only. So we will not perform any right shift here. You can note here, we are not performing the swapping. We are performing the right shift operation. Okay. After that, this 12 is considered. So 12 comes here. Then 1 is compared. Okay. So once again, see here, this 1 is compared with 12. So 12 shift here. Then 1 is compared with 10. 10 shift one position right. Then 1 is compared with 4. 4 shifted one position. Then 1 is compared with 3. 3 is shifted. 1 is compared with 2. 2 is shifted. Okay. Then 1 comes here. So finally you will get this 1, 2, 3, 4, 10 and 12. And finally this 5 comes here. Now 5 is compared with 12. So 12 is shifted. 5 compared with 10. So 10 is shifted. 5 comes with 4. Now 4 is not shifted. So this position is empty. So 5 just place here. Okay. Similarly, you will perform this. See the algorithm now. So this is the insertion sort. How many times this loop is running? Outer for loop. See the example. First of all, we are considering this 3, then 2, then finally up to 6. So n elements are considered. Then how many elements are considered individually? 7 elements are considered. So n minus 1 passes will be required. Okay. So this is the first pass. What we are doing? Here we are considering from 1. Why we are considering from 1? Because see, the index is starting from 0 here. So we start from 1 here. And j is equal to step minus 1. What is j? J is equal to index of this. What is the index of this? Index of this 4 is nothing but 0. Now you will check this condition. While j is greater than 0 and that key is less than or equal to array of j, then we perform this right shift. What do you mean by right shift? This a of j plus 1 is equal to array of j, like array of 6 is equal to array of 5. It means that we are performing the right shift, and j is decremented. J is decremented, j is equal to j minus 1. So this loop is continued till any of the condition is false. When you come out of this loop, then that particular key, which key, array of step, is placed at the suitable position. And what is the suitable position? Array of j plus 1. Okay. This is nothing but the insertion sort. Now see what is the basic best case algorithm, worst case algorithm, and average case algorithm for this. See the best case scenario. Suppose you want to sort the element in ascending order, data given is already in ascending order. Okay, when you start from here, then you compare it with the previous element. So you will not perform any right shift. Directly you come here on the third element. And once again, this element is compared at the element on this position. Then once again, it is compared and it is in the correct order. So no right shift. Then once again, you come here. Then you compare with the previous element. Then no right shift and so on. Okay. So finally, how many comparisons are required? Comparison will be n minus 1 comparison. N minus 1 comparisons are required, and n minus 1 comparisons, and how many right shifting are required? No right shift required, because each and every time when you compare this, so element is in the correct order, so no inversion is there, so number of right shift will be 0. This is nothing but the best case of insertion sort, when number of comparison is order of n and the number of right shift will be 0. Now, what is the worst case? The same. When you perform the element, when you perform the sorting in ascending order, data given in the descending order, or when you perform the sorting in descending order and data given in the ascending order, then each and every time you will get an inversion, then the element is shifted one position right. Okay. So number of comparison and number of right shift, that will be same. The number of comparison will be n into n minus 1 by 2. Number of right shifting will be n into n minus 1 by 2. So the both of these time complexity will be order of n square. This is nothing but the insertion sort. Okay, so same worst case analysis is order of n square. Best case is order of n. Average case time complexity is order of n square. Now we will see some questions based on these asymptotic notations and the sorting. We will see this question one by one, and we can see what could be the approach for solving these questions. Okay, see the first question. Here summation is there. Summation I, it is ranging from 0 to n, and it is I cube. Just see here, instead of I cube, suppose if it is I, then what is the formula for this? The formula for this is n into n plus 1 by 2. So that is nothing but order of n square. Okay. Instead of this I cube, if it would be I square, means 1 square plus 2 square plus 3 square plus 4 square, like this, then what is the result of that formula? The result of that formula will be n into n plus 1 multiplied by 2n plus 1 divided by 6. That is nothing but order of n cube. Now just consider here, when this is I to the power 1, then you are getting order of n square. When this is I to the power 2, I square, then you are getting order of n cube. Now it is I cube. What you will get? You will get order of n to the power 4. Order of n to the power 4. Now, what is the question? The equality above remains correct if x is replaced by. Okay, see the first option. This is nothing but order of n to the power 4. So n to the power 4. if we define n to the power 4 with the help of exact bound, then can we write this theta of n to the power 4? Yes, we can write this because we are providing the exact bound. It is also n to the power 4 and we are also writing n to the power 4. So first option is correct. See the second option. This is theta of n to the power 5. So here this is n to the power 4 and we are saying that it is exact bound of theta of n to the power 5. So this is not correct. So second option is not correct. Now this is n to the power 4 and we are saying order of n to the power 5. So we can say order of n to the power 5 because order of provide the upper bound. So we can also say it is order of n to the power 5. We can also say order of n to the power 6. We can also say order of n to the power 100. All are correct. Okay. So third one is also correct. See the omega one. Omega is basically used for providing the lower bound. Okay. What is the solution of this? Solution of this should be n to the power 4. Okay. Can we say order of can we say omega of n to the power 4? Yes, absolutely. We can say omega of n to the power 3. Yes, we can also say because omega is used for providing the lower bound. Okay, we can also say n square, omega of n square. We can also say omega of 1. That all would be correct. Here, what we are saying omega of n to the power 3. That is also correct. So, among these 1, 2, 3, and 4, which one is not correct? Second one is not correct because in second one we are saying it is n to the power 5 and with which notation? With the theta notation we are saying it is n to the power 5, so that is not acceptable. So first, first, third and fourth, these are correct. What is the solution? Only first, this is wrong. Only second, this is also wrong. See the third one. 1 or 3 or 4 but not 2. Third, C is the correct option. C is the correct option. See the second question. Which of the following is the tightest upper bound that represent the number of swap required to sort n numbers using selection sort? We know that what is selection sort. Selection sort is basically based on finding the smallest element and placing it at the first position. Then find the second smallest, place it at the second position, and so on. What you are commenting on? You are interested in commenting on the number of swapping, not on the number of comparison. Okay. So what you can do in the first pass, you will find first smallest, and after the completion of this pass, you perform the swapping. That is first swapping. In the second pass, you find the second smallest, you perform the swapping. This is the second swapping. In the third pass, you find the third smallest, place it at the third position. This will be your third swapping, and so on. So what it is saying, it is order of how many total number of swapping will be there. Total number of swapping will be n minus 1 swapping will be there. N minus 1 swapping. Okay. N minus 1 is nothing but order of n. Okay. Order of is used for providing the upper bound. So order of n. This is also correct. Order of log n is not correct because log n is lesser than n. So first order of log n is not correct. Second option order of n is correct. Third option order of n log n, that is also correct because n log n is larger than n. That is also correct because we are providing upper bound. We can say n log n also. Fourth option n square. N square is also correct because we are providing upper bound. So n square is also correct. But what it is saying, see this is saying tightest upper bound. Tightest upper bound. Tightest upper bound means the bound provided by asymptotic notation should be tight. Now see, these three notations are there, order of notation. So bound provided by order of n, bound provided by n log n, bound provided by n square. Both all these three bounds will be correct. But which is the tightest one? Tightest one will be option B only. Because if you consider this order of n, so their growth will be similar in comparison with n minus 1 comparison. Okay. If you compare this n log n with n minus 1, so growth of n log n will be larger as compared to n minus 1. If you compare n square and n minus 1, then the growth of this n square will be larger. Okay, so this bound provided by this n log n and n square will not be asymptotically tight. Bound provided by order of n notation will be asymptotically tight. So correct option is B. Now see here, you know what is binary search tree? Binary search tree is a binary tree. In the left, if you consider any particular node, then in the left hand side the nodes will be smaller as compared to root, and in the right hand side the value will be larger as compared to the root. Okay, if you perform the in order traversal, then you will get a sorted sequence. This is the property of BST. Now, what it is saying, which one of the following is the tightest upper bound that represent the time complexity of inserting an object into a BST of n nodes? Okay. If you are aware of the insertion of a node into the binary search tree, then uh, insertion of any particular node in the BST takes place at leaf level. Okay. So generally, if it is a height balanced tree, then suppose if n nodes are there, then the height of the binary search tree will be log n. Okay, because one node is having two children, left children as well as right children. So you can say that if total number of node is n, then the height will be log n base 2. Okay, but this is not the case always, as in case of BST. Suppose if you are having a right skew tree. What do you mean by right skew tree? See one example in which node 1 is there, which is at the root position. Okay, then node 2 will be there. Where this node 2 will be there? Node 2 will be in the right of this particular node 1. Okay, then node 3 is connected. Node 3 will be in the right of this 2. Then node 4 is there. Node 4 will be in the right of 3. Okay, so this tree is nothing but known as right skew tree, in which you can see that in left hand side nothing is there, everything is connected in the right hand side. So you can notice here, if four nodes are there, then what is the height? 4 is the height. In that particular case, if in that particular BST, if I want to insert any particular node, suppose example 5. So 5 is first compare with 1, then you will come in the right hand side, then you will come, then this is compared with 2, then you will get then you will get this and so in that case, total how many comparisons are required? Total number of comparison will be n only. So that is nothing but the tightest upper bound. So generally people commit this mistake and provide the tightest upper bound as log n, because generally they know that height of a binary search tree is approximately log n base 2. So they put this option B as the correct option, but this is not the correct option. Correct option is order of n. If you want to see an example of this, then see this example. Suppose this is the binary, it is also binary search tree. Okay, 10, then 20, then 30, then 40 and 50. Okay, and if I want to insert 60 here, then first of all I will compare from here one comparison, then I will compare here, then second comparison, third comparison, fourth comparison, as well as fifth comparison. So how many nodes are there? N is the number of nodes. So 5 nodes are there, and how many comparisons are required? 5 comparisons are required. So in that case, you will say it is order of n comparisons are required. That's why we are seeing it order of n only. Okay. See one more question. Let W of n and A of n denote respectively the worst case and average case running time of an algorithm executed on an input of size n. So generally the worst case running time is larger, and the average case running time is smaller generally, or it might be same also, but it is not possible that worst case is smaller than average case. So what is the relationship? You can say here average case running time is less than or equal to worst case running time. Okay, you can say average case running time is less than or equal to worst case running time, and average case is denoted by A of n and worst case is denoted by W of n. So what it is saying, which of the following is always true? Now consider this first one. A of n is omega of W of n. Now what does it saying? Which one is larger? W is larger. W is larger. Okay, and this notation omega is used for providing the lower bound. So generally, what you will say? You will say that larger function is omega of smaller function. Larger function is omega of smaller function, but this is not the case. Here it is not a larger function. A is not a larger function. W is not a smaller function. If A would be a larger function and W would be a smaller function, then it would be a correct option. But it is not the correct option. Consider the second option. A of n is equal to theta of W of n. It is also not possible because theta is used for providing the exact bound. It might be possible that average case running time is order of n square and the worst case will be order of n to the power 3. In that case, this is also possible. So we cannot say that it is always it is theta of. If we say that it is theta of, it means that this and this A and W, the growth of these two will be exactly same. This might not be the case each and every time. So option B would be a incorrect option. Then come to option C. Now just consider this option, compare this A and option C. A of what option A is saying? Option A is saying A of n is omega of W of n, and option C is saying A of n is order of W of n. So we can say that this is correct because see, if it is smaller function, A is smaller, W is larger. So we can say larger function is always order of smaller function. A of n is only what is the difference between C and D? In C we are providing big O notations, and in D we are providing big O notations, and in D we are providing small notation. It is also used for providing the upper bound, and small o is also used for providing the upper bound. But D might not be the case always because if we write this D here, then what does it mean? This A and W will not be asymptotically tight always. So the growth of this W would be larger as compared to A always. We cannot say always this because it might be possible that A and W will be same here, as we have already seen in case of selection sort, in case of bubble sort, or in case of insertion sort. The worst case is also order of n square. Average case is also order of n square. So if both of them are order of n square, then this D would be false, because if it is n square, then if we are seeing small o, then it should be starting from n cube only. N cube, n raised to power 4, n raised to power 5, and so on. Okay. Remember the difference between big O notation and small o notations. So correct option will be C. Okay, now consider this. Consider the following segment of C code. The number of comparison made in the execution of for loop for any n greater than 0. Okay. So suppose we don't know how many times this is executing. What you can take a simple value of j and n. J is already defined. J is equal to 1. Take the value of n is equal to 5. Just take the value of n is equal to 5. Now see, how many comparison? This is asking for number of comparison. Now see, j is less than, initial value is 1. So 1 is less than or equal to 5. This is first comparison. Okay. Then j become 2. Now you are saying 2 is less than or equal to 5. This is second comparison. Then you come here. Then j become 4. Once again you come here. Then 4 is less than or equal to 5. This time it is true. Once again you come here. Now 4 become 8. Now once again you jump here. Now you are saying that 8 is less than or equal to 5. This is the comparison, but what is the result of this comparison? It is false. You come out of this loop. How many times you are making this comparison? First time. First comparison is 1 is less than or equal to 5. Second comparison, 2 is less than or equal to 5. Third comparison, 4 is less than or equal to 5. And fourth comparison, 8 is less than or equal to 5. So first three comparison result in true, and the last comparison result in false. So total how many comparisons are required? 4 comparisons are required. Okay. Now see the first option. First option. This is log n base 2. Now you tell me what is the value of n? The value of n will be 5. Okay. What is log 5? Log 5 base 2 will be something 2 point something. Okay. You are taking the upper bound of this. You are taking upper bound of this. So suppose if it would be 2.23, then this 2.23 is get converted into 3 and then 3 plus 1. So total how many comparisons are required? 4. I think this option A is correct. Just check other option also. N is not correct. See this option. For 5 it is 3 only. But how many comparisons are made here? 4 comparisons. So third option is also incorrect. Now see the fourth option. This first and D, A and D options are there that might cause any confusion. Like suppose if it is 5, then log 5 is nothing but 2.23 something. And if you are taking the lower bound of this, then 2.23 is first converted to 2 only. Okay, then 2 plus 1 is 3. So D will give me 3. But what is my correct option? The correct answer is 4. From where I am getting 4? From option A I am getting 4. So the correct option is option A. Correct option is option A. Purposefully I have taken n is equal to 5. I can also take n is equal to 4. Just consider one more example. If I take n is equal to 4, then how many comparisons are required? First comparison is 1 is less than or equal to 4. Second comparison, 2 is less than or equal to 4. Third comparison, 4 is less than or equal to 4. The next comparison, what is next comparison? 8 is less than or equal to 4. How many total number of comparisons are there? Once again, 4 comparisons are required. Okay, so option A is correct here also. The number of comparison made in the execution of the loop for any n greater than 0. Okay, so you can take any value of n. J is already there, so you can perform some sample calculation and you can find the general expression for this. Now see the another question. If f of n is n square log n and g of n is n log n to the power 10, which function is having larger growth? Here what is the dominating term? N square is the dominating term. Here n is there. Okay. So this n square log n will dominate to this. Then which function is having larger growth? F of n is having larger growth. With the two positive function, which of the following statement is correct? The first one. F of n is order of g of n. F of n is order of g of n. Is it correct? No. This is larger function. So we cannot say larger function is order of smaller function. Option A is correct. Option A is incorrect. F of n is order of g of n. This is wrong. Now see the second one. What second one is saying? G of n is order of f of n. G of n is smaller, f of n is larger. So G of n is order of f of n, that is correct. And f of n is not order of g of n, that is also correct. So option B is correct. See the option 3, option C. F of n is not order of g of n, that is correct. But g of n is not order of f of n, that is not correct. G of n is order of f of n, that is correct. Because it is a smaller function, we can write that this is order of f of n. And the fourth one is absolutely This is not the correct option because it is saying both are correct. So what is the correct option? Correct option is option B here. See one more example. Or before this, we can take this example. See, this is very interesting example. F of n is equal to n and g of n is equal to 1 plus sine n, where n is a positive constant. Which of the following statement is correct? Now see what is the range of sine n. Sine n or sine theta is ranging from -1 to +1. Suppose if it is -1, then 1 minus 1 will be 0 and n to the power 0 will become 1. Is it? So this is n and this is 1. See the another possibility, when it is sine theta is equal to 1, so it become n to the power 1 plus 1, so it become n square. What is the extreme? The extreme will be first 1 and it is n square. So first time n and 1 is compared and second time n and n square is compared. Now what we are saying, first is equal to f of n is order of g of n and f of n is equal to omega of g of n. Now you tell me which of this function is having the larger growth, f of n or g of n? Actually, in this case or in this example, we cannot say this surely which function is having larger growth, because it completely depends on this, the nature of this sign, whether it is going in the negative direction or whether it is going in the positive direction. So only one is not correct, only two is not correct, one and two is also not correct, neither one nor two. This is correct, because we cannot say surely whether this is n raised to power 0 or n raised to power 2 will be there. Okay, so option D would be the correct option. Thank you.
हाँ 10, 20. यहाँ पे हर बर्थडे पे एक प्रॉपर एक